This is our last talk of the session. So Dustin will tell us about verified compilation for modular metatheory.
Thank you. Okay. So I'll tell you about the work that I've done on verified compilation with some great undergraduate researchers, Gabriel and Ritam, and my advisor, Chlipala. So this work sort of came out of a couple of core questions. How should we define language extension, and how should we define compiler correctness to be compatible with it? In terms of what we did to achieve this, we built up a metatheory for combining language extensions and compilers, and an inductive characterization of what correctness means for cross-language translation. And to demonstrate our system, as a case study, I built a multi-pass compiler for system F with recursive functions, existential types, and a global heap. And the interesting thing, of course, is that this can be built incrementally, starting out with STLC and adding features. So in terms of thinking about what definitions we want to think about how compilers are verified. And so whatever definition you're choosing for compiler correctness, whatever relation, you're probably thinking about some kind of relation between source programs and target programs. And I'm using the semantic brackets here to indicate a compiler. And the relation is probably proven by induction over your terms. So you'll have a case like this, for the, let's say lambda here, and each other piece of syntax. And those cases will depend on their inductive hypotheses. And what we really want is we want to be able to talk about what happens when we add new features. So let's say that we want to add recursive functions in. So this fixed feature here is like a lambda, but it has a name that it can use to refer to itself, f. And if we want to add this into the language, ideally, we should be able to just add another case to our proof. Add in the case that looks like the one for lambda, but it's for fix. And what we'd like is if we can just verify this case, then great, we have a verified compiler again. But there's a big question, which is, what about all the other cases that we wrote out before? We're working in a different language now, and are they still valid? And this really depends on how we define correctness. So to give you an example of what can go wrong, let's talk about contextual equivalence for a minute. So contextual equivalence is when you define your program behavior in terms of plugging it into a larger context. And so two programs are equivalent if for any context they give you the same result. Now let's think about this program in the framework of contextual equivalence. This is a very simple little function here. It takes in the function f and an argument x. And it evaluates f on false, drops that, and then just runs f of x. So in the simply typed lambda calculus, call twice of fx is contextually equivalent to f of x. Right? We can just pass in the arguments, and then you can notice you have that f of false there. And STLC is a terminating language. So f of false is equivalent to some v. And from there, we can just drop the v. We end up with f of x again. But what about the recursive functions, right? Well, if you add in your recursive functions, you get examples like this. This function f here, if x is true, returns true. But if it's false, it just loops. And so you can see that call twice of f in true isn't going to terminate, even though f of true does. And so what this tells us is that contextual equivalence is not suitable for extension. And what we need is a notion of correctness that's monotonic under language extension. That is, when we add more rules, everything stays the same. All the facts we knew stay the same. So with that framing, let me get into our formalism in Pyrosome. So the core theory of Pyrosome involves languages defined as lists of inference rules. Formally, these are generalized algebraic theories, but you don't need to know about that to use Pyrosome. So we have sort of a couple main kinds of rules. You can write rules like the one on the left, which introduces a new piece of syntax for lambda and gives you the typing judgment. You can also write rules like the one on the right that gives you the equation for beta. And we define equivalence in Pyrosome as the closure over all of the equations defined in a language. So that's reflexive, transitive, symmetric, congruence closure over all the user's equations. And to give you an idea of what the implications are for that, consider this sort of fragment of a judgment here. We're trying to just, again, a very simple example, but just showing what happens if you apply the identity function to true, and you can prove that that's equal to true. Well, as I said, you have the closure operations and the rules. So you can use closure operations like transitivity so that you can break up the reduction to steps. And then you can use rules like the beta rule I showed earlier. And whenever you appeal to a rule, what you have to show is, yes, this rule is in my language L for this judgment to hold. And the great thing about this is that what this means is the only way that our derivations use our language is by membership there. So we can take a bigger language L prime, and this derivation still holds in L prime. Whatever other rules we want to add in, the derivation still holds. And by subset, I literally mean subset of the rules. Now let's get back to compilers a little bit, right? And talk about how we define correctness for compilation. And in Pyrosome, we define that in terms of type and equivalence preservation. So what we're looking for is this type preservation, which is pretty standard, but also equivalence preservation, which says that if E1 and E2 are equal in the source language, well, then once we compile them, the results should be equal in the target language. And this is the key property that we use in Pyrosome. And because equivalence is monotonic, all of this is monotonic. And this also has the benefit of being language agnostic. There's no specific language I'm mentioning here. I'm not relying on any features of the language to define correctness. It also has some very nice properties, just reorganizing it here. If I have another compiler with the green brackets, I can compose them. And just by composition of implication, the composition is a correct compiler. And I also want to point out that I'm doing all of this on equations. So this means it's in an open context. And so what that means is I can do linking, and all the results I have are sound under linking with target code. Now coming back to the idea of proof, because really what we're concerned about is how to make proofs extensible. The proofs are a little more complicated this way, because now I'm doing induction on a derivation of equivalence rather than on a single term. But all that really means is I'm adding in a few extra cases, one for each of the rules, the equational rules that the user wrote. So the case for beta reduction would look like this, and it says if you can compile the applied lambda, that should be equivalent to compiling a substitution. So really, this is just a few more cases on our induction. And again, our goal is now, for adding a recursive function, we should just be able to add some more cases in. And now I can get to how we do that, which is a predicate that I call the preserving predicate, which is an inductively defined predicate that's inductive over the definition of the language in the compiler. So we have a couple cases of rules, right? The case where a rule defines a new feature f, in which case the compiler should have some target term that represents the compilation of f. And the proof goal that preserving requires is that you need to show that target term is well typed, and this corresponds to type preservation. Now, if you have an equation in your source language, there's no new syntax being involved, so you don't have another case of your compiler. But you have one more proof goal, which is to show that, again, the compiled terms, E1 and E2, are related in the target. And the great thing about defining this as an inductive predicate is that if I want to add a new rule to my language, I just add a new case to the inductive. Or I just add a new case to my proof, right? I just call a new constructor of the inductive. And as a theorem, we've proven that this inductive predicate implies the semantic properties I described earlier. So to show a little bit of our case study, I'm going to sort of walk through a portion of the case study compilers. And if you're not familiar with CPS, I would, rather than focusing on the details of the next slide, I would just look at the shape so you can understand sort of what Pyrosome looks like in practice. So here we have the CPS compiler for simply typed lambda calculus. And we have a type translation that translates function types into continuation types. And I use the negation symbol as a type of continuations. So the intuition should be implies false or non-returning function, right? So a function translates into a continuation expecting its argument and a continuation to pass the result to. We compile variables x into calls to the distinguished variable k, which we use to hold the continuation by convention, that just pass x into it. Lambdas are values, so they also get passed to k, and they get translated into a continuation that just lines up with the type signature. And the most interesting case is the application case, which sequences the computation of the function and the arguments, where it evaluates e first and then e prime, calling the result of e with the result of e prime and the continuation. And this is really just using some substitution and continuations, but it's a little more pleasant to read it with the monadic bind. Now, how do we write an extension for this, right? We have our fixed rule, so we'll just add one more case for fixed. And this case is going to look very similar to lambda. And by preserving, all we have to do is add a case for this and then not shown the beta reduction for fix. And if we verify those two cases, great, now we have an extended compiler. So we can put together a bunch of components. I also have a closure conversion pass, and I also have mutable references that go through the same pipeline. And as an example of a feature that doesn't require changing the target language, I have let bindings that can get compiled away in the continuation passing phase. But this is all simply typed, right? And we also want to be a little more complicated in the type system. So we also support polymorphism, but this is a little different because now we're changing the shape of the judgments, right? Every rule we've looked at so far has this judgment form that says we have a term environment gamma and then a type A. But now we want a type environment delta to hold our type variables. So this means that not just adding rules, but we have to change the rules we have. So if we had this lambda rule before, now we have to add the deltas onto it, right? Now, to handle this, this is one nice thing about having this whole framework of deeply embedded rules, is that I wrote a generic function that just operates over whatever language you give it and indexes all your judgments with a variable or with whatever new construct you want to add. And I verified that this generic transformation preserves correctness of compilers. So what we can do is take that whole prior slide and put it in this big purple box with delta that adds a delta onto all those compilers. And by the theorem, all these compilers are still correct. And now we're ready to add in polymorphism. So we can add universal types and existential types. And the CPS pass for those, we actually only need existentials in the continuation calculus. Some of the talks from Olivia Fest maybe have mentioned some of these things. And then we have closure conversion for that. And we also, I haven't talked about it, but we also include in the paper a small linear case study and a small sort of imperative language, just to give you an idea that not everything is based on simply type lambda calculus. We have quite a bit of variety that the system at large can support. So thank you for listening, and please reach out with any questions.
Thanks, speaker. Questions? Any questions? Now you use a compiler in your title. So now can I compile down to assembly all the way?
So I have not done that yet. In the near future, I am interested in connecting this to the Bedrock 2 language that we have in our research group, which is sort of a lower level C-like language. And if I connect to that, then that has a compiler to assembly. So I would like to get there, but not at the moment.
Hi, Max New, University of Michigan. So I've tried to work with things like GATS before, embedded in a proof assistant, and it was a little difficult for me. And so I wanted to know how ergonomic were you able to make it to work with these kind of embedded theories?
Yes, so there's two components to that. One is in terms of writing them down, and then the other thing is in terms of proving things about them.
Yeah.
For writing them down, I have a system. Inside Pyrosome, I have a system for marking arguments as implicit versus explicit. And so as long as you mark the right things implicit, you can write things down exactly as you want and leave it to the proof portion to figure out what those should be. As far as the proof portion, I didn't have time for it in this talk. I have a lot of slides from various points. But I have substantial automation that I built for proving things correct, proving the various goals that I have. And in total, in that case study I showed, there's 127 goals that come out of the preserving predicate. 110 of them are proven totally automatically. The remaining goals, I have designs on how to solve automatically, but generally it involves things like side conditions that the automation doesn't handle yet. But all it boils down to is it takes a lot of work, but the automation is getting there, and really, with the automation, it's quite pleasant.
Okay. And do you use, what do you use for binding? Like de Bruijn?
For binding, I use essentially de Bruijn.
Yeah.
Hi, thank you for the nice talk. I have a bit of a high-level question. So I think one big challenge in compiler verification is verifying optimizations.
Yes.
And I wonder how this framework of extensible compiler play with these optimization verifications.
Yeah, so I haven't done a ton of optimization work. I do have one optimization pass in my current compiler, which is essentially a generic partial evaluation pass that just uses the rules of the language to apply what linear rewrites it can. In general, optimization can have a little bit more flexible of an interface, because since you're usually within the same language for automation, or for optimization, you can, instead of proving equivalence preservation, try to prove just that your input program is equal to the output program. And so this gives you some more flexibility, but I haven't really explored the space extensively yet.
Thank you.
Hi, thank you for the talk. I'm wondering, are there any abstraction or languages that you think are particularly good at being expressed in this kind of framework, in this type system?
Yeah, so the generalized algebraic theory framework was originally designed for dependent type theories. So it's actually very natural to express any of those. In general, I would say type functional languages fit it better, but I've also, to demonstrate as an experiment, done some more imperative type things.
Thank you.
Session. We have the award session and some discussion in the ballroom after. Thanks.
Thank you.